Hello, everyone. In the previous lessons, we, like master chefs, carefully selected the finest ingredients: cement, sand, gravel, and water. But turning these ingredients into a perfect project requires one crucial step in between: cooking. No matter how high quality the materials are, if the concrete isn't mixed properly, transported effectively, or compacted correctly, all that effort is wasted. Today, we're going to talk about the temperament of freshly mixed concrete, its workability. This is the first key checkpoint that determines construction quality. In this lesson, we'll focus on understanding what the workability of a concrete mixture means and the methods for measuring it. The challenging part is identifying the main factors that affect concrete's workability. Only by knowing these factors can we effectively adjust it. Let's approach this lesson with the following questions in mind. Concrete has several key properties: the workability of fresh concrete, and for hardened concrete, its strength, durability, and deformation performance. First, what is workability? Simply put, it refers to how easy a concrete mixture is to handle and place, while ensuring that, once set, it achieves a uniform and dense quality. You should note that workability is not a single indicator. It's a composite property made up of three key traits. 1. Flowability, basically, how well it flows. This refers to the concrete's ability to fill the formwork under its own weight or with mechanical vibration. 2. Cohesiveness, basically, how well it sticks together. This is the ability of the materials to stay tightly bound, preventing segregation or layering during transport and placement. 3. Water retention, basically, how well it holds water. This refers to the concrete's ability to retain internal moisture, avoiding severe bleeding. These three properties complement each other and together ensure the quality of hardened concrete. Now that we understand the concepts, how do we test them on the construction site? The main approach is to assess the consistency of the concrete. Let's take a look at the testing methods next. 1. Slump test for plastic concrete. This is the most commonly used method. We place the concrete into a standard conical mold, level it off, and then lift the mold vertically. The concrete will slump under its own weight. The slump is measured as the vertical distance, in millimeters, that the concrete subsides. The rule is simple: the larger the slump value, the more fluid the concrete, and the better its flowability. While performing the slump test, we should also observe the concrete's cohesiveness, water retention, and sand content to get a more comprehensive assessment of its workability. Based on slump values, concrete mixtures are classified from T1 to T4. The slump test is only suitable for concrete with a maximum aggregate size of no more than 40 millimeters and a slump of less than 10 millimeters. In practice, we choose the slump according to the density of the reinforcement. For example, if the reinforcement is dense or if the concrete needs to be pumped, a higher slump is required. For pumping, typically 150 millimeters or more, to ensure the concrete flows smoothly into place. 2. VB consistency test. What if the concrete is very dry, slump less than 10 millimeters, and doesn't slump? In that case, we use the VB apparatus. Its principle is based on time. We turn on the vibrating table and record the time, in seconds, it takes for the concrete to be flattened and for the surface to appear slurry-like. Here, the rule is reversed. The longer the time, higher the seconds, the harder it is to compact the concrete, and the worse its flowability. Generally, the VB test is suitable for concrete with a maximum aggregate size of no more than 40 millimeters and VB times between 5 to 30 seconds. Based on VB consistency, concrete can be classified as extremely stiff, very stiff, stiff, and semi-stiff. There's also a B-funnel test. The operation is simple. Fill the funnel with concrete, open the bottom gate, and observe how the concrete flows out. The faster it flows, the better its flowability. If the concrete has poor cohesiveness, segregation occurs. Coarse aggregates settle at the bottom of the funnel, blocking the flow of the concrete above. Think about this. What problems can arise if concrete has poor workability? Next, we'll take a closer look at the 4 core factors that affect concrete workability. Since concrete is made up of multiple materials, the proportioning of these materials is naturally critical. We will focus on the amount and consistency of the cement paste, the sand ratio, the properties of raw materials, and environmental factors. Let's examine them one by one. Factor 1. The influence of cement paste quantity and consistency. First, let's look at the cement paste. You can think of the cement paste as the lubricant between the aggregates, and its effectiveness depends on 2 aspects. 1. Amount of paste, thickness. This refers to whether the paste layer coating the aggregate is thick enough. The thicker the coating, the lower the friction between aggregates, and the smoother the concrete flows. 2. Consistency of paste, dryness or fluidity. This refers to whether the paste itself is stiff or fluid. Obviously, the more fluid the paste, the better the flowability. This brings us to a key principle. Whether we increase the amount of paste or make it more fluid, it ultimately comes down to the unit water content. In short, the more water per unit of cementitious material, the greater the concrete's flowability. Experiments have shown that, with a given aggregate type, if the unit water content remains constant, changing the cement content by no more than 50 kilograms per cubic meter has little effect on slop. This principle is commonly known as the constant water content rule. Using this rule, we can fix the unit water content and adjust the water to cement ratio to achieve a mix that meets both workability and strength requirements. Factor 2. Sand ratio, filling and specific surface area. The sand ratio refers to the proportion of sand by mass in the total aggregate. When the sand ratio changes, the total surface area and voids of the aggregates also change, which affects workability. Too high a sand ratio, excess sand dramatically increases the total surface area, absorbing a lot of cement paste, reducing lubrication, and making the concrete dry and stiff. Too low a sand ratio, too little sand cannot fill the voids between the coarse aggregates, causing cement paste to be lost and leading to segregation. Thus, there is an optimal sand ratio for proper workability. The optimal sand ratio is defined as the sand ratio that, under a fixed amount of cement paste, maximizes the mixture's flowability while maintaining good cohesiveness and water retention. Alternatively, it can be defined as the sand ratio that minimizes cement content while achieving a given flowability and strength with good cohesiveness. The diagram on the left shows the relationship between slop and sand ratio. We can see that as the sand ratio increases, flowability decreases, so it's generally better to use a smaller sand ratio. However, the diagram on the right shows that the amounts of cement and sand follow a certain proportion. As the sand ratio decreases, the required cement content also decreases. When the sand ratio reaches a certain point, cement usage is minimized and slump is maximized. This point is considered the optimal sand ratio. Next, let's look at Factor 3. The influence of the properties of constituent materials. First, the cementitious materials. Those with higher water demand reduce flowability, but they increase cohesiveness and water retention. Next, the aggregates. If the aggregates are well graded and contain few flaky or elongated particles, the resulting concrete will have good flowability, cohesiveness, and water retention, and it will be less prone to segregation and bleeding. Therefore, when selecting aggregates, priority should be given to well-graded materials with minimal flaky or elongated particles. Additionally, if the aggregates have smooth surfaces or larger particle sizes, concrete flowability will increase. As for admixtures, adding a water-reducing agent improves concrete flowability. Adding an air-entraining agent enhances flowability, cohesiveness, and water retention. Finally, let's examine Factor 4, the effects of temperature and time. From the diagram on the right, we can see that as temperature rises, the slump of both coarse and fine aggregates decreases. This is because higher temperatures accelerate cement hydration, causing the concrete to set and harden more quickly, which reduces slump. At the same time, higher temperatures increase water evaporation, further lowering concrete flowability. From the diagram on the left, we can also observe that over time, ongoing hydration causes slump to decrease. Now that we understand the factors affecting workability, let's look at how to improve concrete workability. If the slump is lower than the design requirement, we can maintain the water-to-cement ratio and increase the amount of cement paste. If the slump is higher than the design requirement, we can maintain the sand ratio and increase the aggregate content. Can we simply add water to adjust workability? We can see that if we keep the cement content constant and add water alone, the water-to-cement ratio increases, which reduces concrete strength. Therefore, adding water alone is strictly prohibited. In addition, to improve concrete workability, we can use the optimal sand ratio, improve the grading of sand and aggregates, and select appropriate admixtures. Finally, let's look at a real-world case. At a construction site, the delivered concrete was too dry and could not be pumped. To save effort, some workers suggested adding water directly into the mixer. Remember, this is absolutely prohibited. Adding water alone will directly disrupt the water-to-cement ratio, significantly reducing concrete strength and potentially causing safety hazards. The correct ways to adjust workability are as follows. 1. Maintain the water-to-cement ratio and increase the cement paste amount. Although slightly more costly, this ensures the concrete strength and durability. 2. Use a water-reducing agent. This is the most economical and effective method, instantly improving flowability. Conversely, if the concrete is too fluid, we can keep the sand ratio unchanged and add an appropriate amount of sand and aggregates to absorb excess water. That concludes our lesson on the workability of fresh concrete. Looking back at the questions we posed at the beginning, can you now answer them? Let's summarize today's content. When it comes to the workability of fresh concrete, you should remember the 1-3-2 rule. One core goal: make the concrete easy to work with while ensuring density. 3 performance indicators: flowability, measured by slump, cohesiveness, and water retention. 2 key variables: adjust flowability primarily through water content or water-reducing agents, and adjust cohesiveness mainly through the sand ratio. I hope that in your future engineering practice, make sure to never add water arbitrarily and become a competent concrete mixing engineer. That's all for today's lesson. See you next time.